Okay, today we will discuss about transport layer congestion control, second part. That is, in the first part we discussed about data traffic, traffic policies, traffic descriptor. Then we have discussed about open loop and closed loop congestion control policies. Now we will a little bit elaborate about congestion control by considering two examples. Our objective is to study congestion control in TCP, some sort of overview we will take, and second one is congestion control in frame relay. So these two methods we will talk about. So in general, congestion policy as far as considered in TCP, if we think about in process to process communication, then it is based on three phases in TCP. First one is slow start. First one is slow start. Second one is congestion avoidance, and the third one is congestion detection. So all these three categories are supported. In the slow start phase, the sender starts with very slow rate of transmission and increases the rate rapidly to reach a threshold. And when threshold is reached, the data rate is reduced to avoid congestion. Finally, if congestion is detected, then the sender goes back to slow start or congestion avoidance phase based on how the congestion is detected. Now here you can see in the diagram that is a round of transmission. So in the beginning, it has started with single frame, so single segment. Red portion you can see 2 raised to 0, then CWND, that is your congestion window, and that is 1. Then the segment is transmitted, acknowledgement is taken. The acknowledgement number, that yellow boxes you can see, it is indicating 2, that is inclusive acknowledgement. The receiver is indicating that it is expecting second segment. Then in the second part there will be CWND 2 raised to 1, that is 2, and the second segment is sent. Now it is expecting the next segment, so therefore acknowledgement 3, ACK3 is sent back. So this way slowly it is going to proceed. Simple thing, it is based on the size of congestion window. This mechanism start with one maximum segment size, that is in the beginning. Then the slowly the during the congestion establishment, one by one the size of the window is increased when the acknowledgement is received. As the name, in the name we have mentioned, it is exponential increase. So therefore we are progressing with exponential figure, that is 2 raised to 0, 2 raised to 1, 2 raised to 2, and so on. So like that. So we have assumed in the beginning that is your RWND, that is receive window, is much higher than the congestion window, so that the center window size always equals CWND, that is congestion window size. Then receiver window size and your congestion window size, slow gradually there is a progression. The sender starts with 1 and then it progresses, and we can see that in the figure we have as just a progression part, we have mentioned up to CWND 8, that is 2 raised to 3, and the size is 8. So the segment number 7, up to that we have reached. In round 1 1, round 2 2 raised to 1, round 3 round 3 4, like that, 2 raised to 1, 2 raised to 2, 2 raised to 3. So like that we can progress. And here it is slightly, that is acknowledgement is as the size increases, so accordingly the acknowledgement is mentioned. So in the beginning, slow start threshold, and then the size of the window in bytes reaches this threshold, so slow start stops and next phase starts. So in most implementations, this may go up to 65535 bytes and so on. So this is in general slow start algorithm. The size of the congestion window increases exponentially until it reaches the threshold. This is a simple strategy. Then next one is congestion avoidance type, additive increase. Here in the figure clearly you can see round 1 2 3. So in round 1 it is congestion window 1, then in round 2 it has become 1 plus 1, additive manner. So 1 plus 1 2, accordingly the acknowledgements are given. Then in round 3, so there 2 plus 1, that is 3, so CWND is becoming 3. Then next 3 plus 1, that is 4, and so on. So segment 1, segment 2, segment 3, 4, 5, 6. So like that appropriately there is a transmission from sender and different rounds of transmission, and then appropriately the acknowledgements are received. Here, after each round, we are adding and simply it is increased by 1. In this case, the congestion avoidance algorithm, the size of congestion window increases additively until congestion is detected. Then the implementation reacts to congestion. That is the next thing is detection in one of the following ways. That is, the detection is by timeout, a new slow start phase start. You can or the second one is the detection may be with the help of 3 acknowledgements. So this is the new congestion avoidance phase. So these are the 2 facts which are carried out. So congestion detection is the first and then congestion avoidance policy. Now multiplicative decrease it may be. So if congestion occurs, the congestion window size must be decreased slowly. Then the only way the sender can guess that congestion has occurred is by need to retransmit a segment, because it is not going to receive the acknowledgement. The retransmission can occur in one of 2 cases: when a timer times out or when 3 acknowledgements are received. In both cases, the size of threshold is dropped to 1/2. This is the actual working principle. So this is called multiplicative decrease. Most TCP implementations have 2 reactions in this case. First one is timeout occurs. There is a stronger possibility of congestion. Segment has probably been dropped in the network and there is no news about the next segment, which segment has been sent. In this case, TCP reacts strongly. It sets the value of the threshold to 1/2 of the current window size. So we will go to that particular figure. Before that, just you can have a look that in the beginning, that is SS threshold is equal to 1/2 the window and CWND is 1 MSS. So maximum size. Then timeout, slow start. Then if it is greater than that, then it will proceed. Once again, window size is divided by 2. Then again, it will enter into congestion avoidance phase. Then it will continue. So like that. So this can be just visualized here. So it sets the value threshold, that is to half. In the beginning, it is the 16 somewhere. Then the slow start. Then there is additive increase, and then there is a multiplicative decrease. It is suddenly coming down, you can see. So in the beginning, that blue portion SS slow start portion, it increases, the threshold value is 16. Then there is a additive rise, then there is a timeout. So after that timeout, then slowly it is going to come down the threshold, and the threshold is now 10. So again, because of multiplicative decrease, it has come down. Again it will start slow start with threshold 10. Then again it will receive 3 acknowledgements. Again it will come down. So like that, it is just the general mechanism. So we can see that just in the beginning it is set to 16. Then 1/2 of the maximum window size, it is 32 if we take, then it is made half of that. In the slow start phase, the window size starts from 1 and grows exponentially until it reaches the threshold. So that blue part, beginning part. And then after it reaches the threshold, a congestion avoidance procedure allows the window size to increase linearly, then until a timeout occurs, that is with respect to maximum window size. Then the timeout occurs when the window size is 20 approximately. You can see the yellow portion, linear part, that ramp portion with black dots and pink line, and that timeout is written at approximately on the y-axis if you check. So it is approximately at 20. At this moment, the multiplicative decrease procedure takes place and reduces the threshold to 1/2 of the previous window size. So previously it was up to 20. From 16 to 20 there is an increase. Then 20, half of that, it is made now 10, and then it will proceed. So TCP moves to slow start, again starts with window size 1. TCP moves to additive increase, then again new threshold is reached, and approximately it is 12. So here you can see the last yellow portion, that is the additive increase portion, and it is reached approximately up to 12, and then again it will come down, and another whenever it is going to get continuously, that is 3 acknowledgements. So one by one it will proceed. Then for congestion control in frame relays, this is the second example we can just comment on that. So in frame relay network, congestion decreases with respect to throughput, and that is going to increase with respect to delay. High throughput and low delay are the main goals of frame relay protocol. That is the main thing. Frame relay does not have flow control. Frame relay allows the user to transmit bursty data. This is very important. This means that frame relay network has the potential to be really congested with traffic, thus requiring congestion control, because burst data is handled by frame relay. So by default, that is a probability. Now here for congestion avoidance, frame relay protocol uses two bits. One bit is called as backward explicit congestion notification, and that is BECN, and second bit is called as forward explicit congestion notification. So in the figure you can see this is BECN, that is backward explicit congestion notification. This bit warns the sender of congestion in the network, about the congestion in the network. You can see here that there is a directly, the figure is showing clearly that how it is accomplished. In between, the switch can be used to give the response, or else the switch can use a predefined connection. Separate connection can be set, and with that you can send that particular bit, like it is coming back. So in general, if whenever there is a congestion, in the direction of congestion is just noted on the figure, and exactly opposite to that there will be that BECN bit, that is backward explicit congestion notification is given. In the same fashion, in case of forward explicit congestion notification, here also there is a warning sort of thing. The only thing is that here the warning is not to the sender, warning is to the receiver. So that's why it is in forward direction. It is in the same direction of congestion. So same procedure. It might appear that receiver cannot do anything to relieve the congestion. So frame relay protocol assumes that the sender and receiver are communicating with each other, and they are using some type of flow control at higher level. So if there is acknowledgement mechanism at this higher level, the receiver can delay the acknowledgement and thus forcing the sender to slow down. So delay in that acknowledgement is indicating that there is congestion. And if you club together like all the four cases of congestion, so if there is a no congestion, then definitely your FECN and BECN bits, both of them are 0 in forward as well as in backward direction. If there is a congestion in the direction from sender to receiver, that is A to B, then backward explicit congestion notification is given, and that bit is set 1 while the frame is transmitted from A to B. That FECN, that is forward explicit congestion notification bit, is set to 1. Whenever it is from B to A, BECN is 1. Whenever it is from A to B, FECN is 1 in figure B. In figure C, there is a congestion in the direction B to A. So here in the beginning, from B receiver, there is FECN, that is in the opposite direction to the source it is intimating. So that FECN bit is set, and from A, because direction is B to A, so therefore from B to A there is a forward, and from A to B there is a backward. And in figure 4 there is a congestion in both directions. So both of them, sender as well as receiver, they are going to set BECN as well as FECN. So all together, as if there is a sort of a suspension will occur, and the congestion to certain extent will be avoided.